So now let's consider a one-dimensional problem. When we started one-dimensional actually loaded members, and we also considered similar exam problems here. Okay, but instead of just forces in the longitudinal directions, and then now we want to consider torsional moments. Now we want to consider torsional moments here. For example, at this point we have T1, and then at this point we have another one, and at this point we have T3. So we may have multiple torsional moments here. But before start our analysis, what we have to do is we need to consider the free body diagram, because we want to consider the three conditions sequentially: the force equilibrium, the material law, and displacement compatibility, isn't it, right? So here we want to consider a free body diagram. So generally speaking, let's say let's consider this cross section here. Say then we have the part of the structure here, or part of a structure here, and then this part of structure is subjected to internal torsional moment, T. Okay, so make sure that here the difference is this guy is external ones. Okay, this sign convention must follow the choice of coordinate system, but this guy is internal. Okay, similar to the internal force N that we introduced in the discussion of actually loaded members. Okay, similar to this. Okay, so now we have a segment of structure, but it's subjected to twisted moment. Okay, because of this twisted action, so we may have some kind of rotation, isn't it? We may have, if you look at the structure here with some dimensions. So here I want to consider left hand side is the reference point. This is equal to 0 here. We introduce new coordinate system. Let's say the length is equal to L. Now let's keeping the reference rotation at this point is phi is equal to 0. Then because of rotation, at this point the rotation angle phi is equal to 0. But as we considered more lengths, then the phi linearly increases, isn't it? The linearly increases such that the end of this member, for example here, then the rotation angle should be maximum phi. Okay, then let's look at the cross section. If you look at the cross section, then because of rotation, let's say this line is rotated to this line P, which means the point at first was here, move to the next position, isn't it, right? This is the displacement. Then how do you calculate that displacement? This displacement is equal to this displacement, let's say delta is equal to the radius r, radius r times the rotation angle phi r, isn't it? And then here let's define the shear strain. How do you define the shear strain? Do you remember the engineering shear strain? Let's say we have a block here, and if this block is displaced by delta, then engineering shear strain gamma was defined as well. Let's say height, the gamma was defined as delta divided by h. That was the definition of shear strain, the measure of distortion. The similar discussion is applied to here. So how do you measure the lateral displacement? The lateral displacement delta is here, and then the height, this is the height, and this is the height, isn't it? Then we are ready to calculate the shear strain. The shear strain gamma, shear strain gamma is equal to the lateral displacement delta is equal to phi and the radius r, and divided by the height. Height is the radius, isn't it? By the way, no, sorry, I was confused. Sorry about it. And then sorry, I was confused. And then let's look at here. So I'm talking about here. So initially we have a straight line. So let's say, as given in the lecture note, P and Q. Okay, P and Q. Let's say point Q is here. And then let's imagine that we have rotation angle phi. And then because of this rotation, Q is displaced to Q prime. And then this is the displaced position Q prime. Okay. So initially the straight line in the direction of in the longitudinal direction of the member is displaced to this this blue line. Okay, let's look at the discussion here. So here the elongation, not elongation, the change delta is, as I told you, phi times the radius r. And then how about the height? The height is here. This is the height. Okay, so here the height is equal to length L. That's why the shear strain is gamma is displacement and the height, okay, to measure distortion, and this is equal to phi r divided by the length L. Is it clear, right? So this is the shear strain that we can measure on the surface. Make sure that this is the shear strain that we can measure on the surface. Shear strain on the surface. So why we say that this is shear strain on the surface? For example, the amount of displacement depends on what? The radius, isn't it, right? Depends on radius. So what if you measure, the displacement at midpoint, for example here, for example 50% of the radius, then of course the displacement becomes half of it. That's why the shear strain becomes half of it, isn't it? Now how do you measure? What if you measure the shear strain at the center of the cross section? The center of cross section, R is equal to 0, then shear strain is equal to 0. In the case of circular shaft, the shear strain at the center is equal to 0. There is no shear strain at the center. Okay, the measure of shear strain. This is measure of shear strain. So if you look at this formula, I have a length unit, and also I have a length unit. Okay, and then here length unit, then if you check the unit of the shear strain, the length divided by length is dimensionless. The shear strain is dimensionless. Okay, dimensionless. And then here we have new terminology, theta. Theta is called rate of twist. Theta is called rate of twist. This is the rate of twist is defined as the change of angle of twist divided by the reference length, then which provide unit angle of twist. This is the rate of twist. Then the maximum shear strain, gamma max, can be given by with this new notation, radius times the rate of twist. So now we just work for this part. Okay, we just discussed displacement compatibility. And then first we define the displacement field using angle of twist, using the angle of twist. And then from this angle of twist, we derive the information of shear strain here. Okay. Okay, let's check hollow section here. If you check the hollow section, so as we discussed, the shear strain is linear with respect to distance measured from the center. That's why the shear strain at arbitrary point has a linear relation. So the shear strain is proportional to the distance. The rho is distance measured from the center, and then it is divided by the maximum radius of the section, and then it is scaled by the maximum shear strain. So let's consider this hollow tube, circular tubes here. So maximum one is, instead of rho, we put the maximum radius R2, here R2. And then the maximum shear strain was given in here. Okay? And then the minimum shear strain, because here is empty, the minimum shear strain should be here. So make sure the distribution of shear strain is linear. That's why instead of rho, we put the inner radius R1 here. Although in our textbook it's given as R2 and R1, but in many textbooks R2 is denoted by the outer radius, R out, and the R1 is denoted by Ri, the inner radius. This is outer radius, inner radius. Okay, then what's the next step? So we just finished, up to the displacement compatibility. So we were able to, first we define the distribution of we prescribe, for example, let's say X, and then we define the displacement field using the angle of twist, let's say 0.1 A, B, C, whatever. And then probably we have arbitrary distribution of angle of twist. Okay, and then once we have angle of twist, then we can measure the change of angle of twist in AB segment is equal to what? The AB segment is equal to PB minus PA, because we are using this coordinate system. Okay. And then the angle of twist in BC segment can be calculated by PC minus PB, isn't it right? It is not PB minus PC, okay? Because of choice of our coordinate system. So once we have this change in angle of twist, then we can calculate the maximum shear strain. The maximum shear strain, gamma max of AB segment is, how do you calculate this? The maximum shear strain is radius of AB segment, and then the change in angle of twist of that segment divided by length of that segment, isn't it? So here we have formula. Okay, this is a calculation of shear strain. So now we are here. So we can define this relation at any place. For example, that is for here, isn't it? And also we can do the same thing for BC segment 2. We can do BC segment 2, and also here too. Okay. So now next step is we need to check the constitutive relation between the stress and the strain. So what stress we have? Instead of normal stress, I have shear stress. And then instead of normal strain, I have shear strain. Okay. So between the shear stress and the shear strain, we still want to use Hooke's law. So Hooke's law is nothing but just linear elastic relation. The shear stress is proportional to the shear strain. So shear stress is proportional to engineering shear strain. The proportional coefficient, so I'd like to choose G, gamma. And this is called shear modulus. Okay, or in other words, we call it elastic shear modulus. The same meaning. And then if you plug the information of shear, the shear strain here, last time that we calculated shear strain at arbitrary point, for example here and here, then where is it? My shear strain is proportional to the position, the radius. Okay, so proportional relation. That's why it is equal to rho divided by the maximum radius and then the maximum shear strain. That's why we have this expression. And then where we have the maximum shear stress, the maximum shear stress is what? When rho is equal to the radius, it is cancelled. This is equal to shear modulus times maximum shear strain. Okay, shear modulus times maximum shear strain. Then what's gonna be the shear stress at the center of the cross section? If rho is equal to 0, then my shear stress is also equal to 0. So make sure that the distribution of shear stress on the cross section is linear. The shear stress tau is, at the center is equal to 0, and on the surface it is equal to maximum the shear stress, and between the surface and the center there is a linear distribution. Any questions? So now we finish it here. Okay, we discussed here. So now let's talk about the force equilibrium. The force equilibrium between the torsional moment and then the shear stress. Let's talk about this. Okay, so now as we discussed, the distribution of shear stress is linear, is it right? Distribution of shear stress is linear. So if you imagine this cross section, let's imagine that we have a section here, then we have some distribution of shear stress, okay, isn't it? And then the contribution of all this shear stress on the cross section produce the torsional moment. Okay, so torsional moment of the cross section is the integration of all the small torsional moment. Then how do you calculate this small torsional moment? The small torsional moment is what? We need to consider small segment, and then we need to calculate the torsional moment acting on this small segment by shear stress. Okay, for example, so small torsional moment small torsional moment caused by the shear stress acting on this material point is equal to what? The first torsional moment is what? The force times the arm length, isn't it? So the shear stress times this area is equal to the force. And then it is multiplied by the radius, rho. And then the information of shear stress was calculated here. The shear stress is linear with respect to the radius. So let's plug this information into this expression. And finally, we have maximum shear stress divided by the radius, and then we have maximum radius, and then radius square of the radius to the position where we calculate the small torsional moment, and then multiplied by the fraction of area. So now we want to integrate this small torsional moment for all the material points over this cross section. So the total torsional moment is the integration of small torsional moment over the cross section. Make sure that we are talking about circular section, which means the maximum shear stress is independent of the position. That's why we can take out from this integration. And also the maximum radius is independent of the position. That's why we take out these two quantities from this integration. So finally, we have this quantity. And this quantity is called polar moment of inertia because we integrate square of the radius of the cross section. This is called polar moment of inertia. So polar moment of inertia in 우리말 극관성 moment. Okay. Then what's the relation between the polar moment of inertia and the second moment of inertia? Okay, then to understand this, because of Pythagorean theorem, the radius square is equal to nothing but just x square plus y square, isn't it? So if you plug this expression into here, and then we can separate integration of x square plus y square over the area. This is equal to x square over dA plus y square over dA. The first one is second moment of inertia with respect to y-axis. This is second moment of inertia with respect to x-axis. Okay. Simply speaking, the calculation of polar moment of inertia is very easy. Okay, just sum of the second moment of inertia with respect to y direction, y-axis and x-axis is enough. Okay. Okay, so now once we have the torsional moment acting on the cross section, and then we have maximum shear stress, then we can build up the relation between the maximum shear stress and then apply torsional moment. So let's move all these quantities to the left hand side. Then finally the maximum shear stress caused by torsional moment can be obtained by this formula. The further, let's use this proportional relation between the maximum shear stress and then shear stress. So let's plug the information to the place of maximum shear stress. If you do that, my shear stress is given by this expression. Okay, so let's look at this equation more carefully. And my shear stress, as I told you, shear stress is linearly proportional to the distance measured from the center of cross section. Linearly proportional to the distance. And then also, if you have higher torsional moment, then my shear stress increases, isn't it? This is also proportional to this. And then if you have bigger cross section, for the same torsional moment, then my shear stress should decrease, isn't it? So it is inversely proportional to the measure of cross section. Here the second moment of the polar moment of inertia. So if you combine all these relations, my shear stress can be measured by the radius times torsional moment and divided by polar moment of inertia. Okay, this is the easy way to memorize this formula. So you better memorize this formula, and this formula is very useful, which provides us the relation between the shear stress and the upright torsional moment and some geometrical the information of the cross section. So as I told you, we want to use the three conditions. The first one is we want to use kinematical comparability. The maximum, the shear strain can be obtained by the change in the angle of twist of the segment, and it should be divided by the length of the member, and then we multiply this ratio by the maximum radius to the surface of the cross section. And then we use the constitutive relation. The maximum shear stress is equal to the shear modulus times the maximum shear strain. So let's plug in here. Then we can obtain information of maximum shear stress. By the way, I have an error, so let me fix it later. But what I want to say is this guy, okay? Tau max is equal to T is equal to IP divided by radius tau max. And this expression should be placed here. Okay? So if you combine all these three conditions, we can derive so-called torsional formula. So torsional moment is given by this expression. Torsional moment is given by shear modulus polar moment of inertia divided by length and then change in angle of twist. So let's compare this equation with what we derived in the section of actually loaded member. The internal force is equal to the elastic modulus and the cross-section area divided by the length and then what? The elongation, isn't it? So if you check the structural formula, they are very similar to each other. The first one is what? This is material parameter, isn't it? Okay, and then both we have the length measure, right? And then IP is measure of cross section. Area is also measure of cross section, isn't it? And then here elongation. What I mean, the difference in the displacement. And then here difference in the angle of twist. Similar to this. This is a measure of deformation, isn't it, right? Measure of deformation. And then here, this is the internal force. Internal force. Now how about this? Internal torsional moment, okay? Not the external one. Internal torsional moment. So what is this guy? How do you call this guy? We call it what? We call it the stiffness, isn't it, right? Stiffness. Stiffness of actual loaded member. And then what is this? This is stiffness of torsionally loaded member. So there is very close similarity in the torsional problem to actually loaded members. So this is called torsional formula. So if you represent the torsional formula with respect to the change in angle of twist, then it is given by TL divided by shear modulus and the polar moment of inertia. So let's compare this equation. Delta axial force, the length, the elastic modulus, and the cross-section area. Yeah, they are very similar, isn't it, right? And then here GIP is called torsional rigidity. The EA was also called rigidity, okay? Very similar. So as I told you, this is torsional stiffness. And then the inverse of this is called torsional flexibility. So now instead of solid circular section, let's talk about the same problem for the circular tube. The principle is exactly the same. So we want to use this formula, but here the shear modulus is same, and then the length is same, and then the change in angle of twist is same. Only difference is this polar moment of inertia, because last time we had a solid circular section, so now we have hollow section here, so we have to subtract the hollow part. So this is the formula for the second polar moment of inertia of circular section, and then this is the outer part and this is the inner part. So instead of radius we can use the diameter, same meaning. So if you consider very thin section, then instead of using the outer radius and inner radius, so we may want to use just average radius, okay? If you simplify this equation, taking into account the fact that the thickness is very small compared to the radius. So saying again, in engineering practice, instead of R2 and R1, we use outer radius, the inner radius, okay? And how about in practice, let's consider a very thin tube. When we represent diameter, for example, the diameter of the section, like let's say this is phi 1000. The phi 1000 means its diameter is 1000. Now, does it represent the inner diameter or outer diameter? Typically, we use the outer diameter as a reference one. This is 1000. And then it is given by the thickness T10. T10 means the thickness is 10 millimeters. This is thickness. Okay? This is a way of representing the dimensions of pipe in practice. So here, let me take another 10 minutes break.